All right, let's go ahead and get started. So I do have I don't know if it's going to be a spectacular demo. I was playing with a lot of compounds. I'll kind of explain what's going on here. But I'm going to save the mirror demo probably for next week, the plating the mirror, just because I already dragged out like half the lab. But we'll look at this fun stuff. All right, so let's continue. So just some more definitions. And so we have what's called these chelating ligands, or sometimes called polydentate ligands. And so chelating just means that you can throw a metal on there. And so oxalate would be another example. Again, you have these oxygens, right, donating electrons to your metal center. We had mentioned with our naming this ethylene diamine, and I was looking for some ethylene diamine. Unfortunately, we don't have any on hand. I tried a substitution, but I don't think my substitution went well, but you can look at the mess I created. And then we have other kind of bidentate ligands. So this would be, so bi, meaning that it's binding at two places, and this is another common framework. This, again, two amines and some sort of backbone, or sometimes you could also have this phenyl ring backbone, and then these kind of amine pincer ligands. So these are also called like pincer ligands. Those are pretty common. And then you can also have tridentate or other complexes. So this is crown ether, these sorts of complexes that have these, right, some sort of organic ether and kind of repeats. And they can come in different lengths or different sizes, and so you could kind of tune your crown ether size to whatever you're trying to capture. And so then we can start looking at some isomers, which this will probably help you with that one pot lab if you haven't already puzzled through it. And so let's start. We're going to focus on our square planar isomers first. So this is all for square planar. And then we can have the cis isomer where they're on the same side. So the same groups right on the same side, compared to the trans isomer where the same groups are on opposite sides. Oh, let me turn my boiling down just a hair. So now trans is opposite. And so this is pretty significant, these two differences. So you would be able to tell the difference between these two. So we'll kind of get into how. One other way that you can tell, now I lost my window. Sorry. Where'd it go? Here it is. So this is an example of how you would distinguish between these two isomers. So of course, right, if they're different colors and you already have them like characterized for colors, obviously that could be one way, like we've done just like that with that blood red complex, right? We can characterize it. But another thing that's commonly used is if you have like a carbonyl on there, which people often study carbonyls since they have pretty distinct what are called IR stretches. And so kind of the long and the short of this, because then this gets into a little bit more advanced like MO theory, but we've kind of seen this before, right? We've seen that, okay, the geometry and the symmetry mean different things. And we'll skip to the conclusion of this. And so it's saying, okay, we can distinguish between our two isomers using IR or Raman spectroscopy. And it says that our cis isomer produces 2 CO stretches in our IR, while the trans only has 1, which kind of makes sense if you think about it, right? So cis, it's more asymmetric, so you're going to have different stretches from either them both going out or the asymmetric. So that gives you kind of 2 bands versus this trans, right, where it kind of cancels out, so you only see 1 stretching frequency. So that's just an example, like I said, of what you might potentially do in inorganic chemistry, how you would distinguish them. And then from there, right, you would make an MO diagram, maybe do your research paper, right, HOMO-LUMO gap, and then colors. And so then other isomers is, so we could have now for the octahedral complex, we can have the same sort of cis and trans isomer. So again, where you're looking at these 2 chlorines are next to each other, and that's cis. And then of course we can rotate it, right? They could be here and here, here and here, here and here. All that would still be cis, versus across from each other, they would be trans. And again, you would see this reflected in their MO diagram or stretching frequencies. So same sort of concepts, right? Where we have symmetry in the trans versus asymmetric in the cis there. And then the next type that we can have, and so this is for octahedral specifically. And I did make models that we can pass around. So we have, and so your book uses this term that actually I've never seen until your book. And so it refers to this isomer over here as cis-cis, since you have, right, 2 kind of cis relationships. But the way I've always learned it is FAC, kind of meaning like a facial relationship where they're all on the same plane or face. So I'll hold it for the camera. So I'll pass this around. So again, this is FAC going around, so you can kind of rotate it, see it. I'll start this one over here. And then MER. So I know this as MER from the mirror plane. So right, the same substituents occupy the same mirror plane. They highlighted the amines. I'll say same mirror. Oops. But again, your book uses the term that I'm not, I mean, we can puzzle it out, but again, I've never seen this used in literature. It's usually, oh, it's FAC and MER when they're referring to these geometries. But your book calls it cis-trans, which you can see, right, we have a cis relationship and a trans relationship as well. And so I did build that one. Sorry, I didn't put my atoms on very well. So there's for the camera, and then I'll start our MER on this side over here. So you can just rotate. There's MER. And so then there's other sorts of isomers. So this one, it's called a linkage isomer. So basically it changes how it's bound to the metal. So on this end, it's bound by the nitrogen. And then I'm not sure how you would go between these 2 particular isomers. But then you could switch to the oxygen here. Let's see. I should have shown, I didn't get an example of this, but another common kind of linkage isomer is going to be like ethylene, and so it can also bound either side bound here or other ethylene-like complexes, right? Or it could bind directly to the metal. I'll just call this kind of head on. So those would be examples of linkage isomers. And again, you could see other kind of common things. I'm surprised the nitrogen couldn't also do sidebound. Maybe it could in another compound. All right, and then you also looked at optical isomers. And so then optical isomers have some sort of chirality and then mirror image. So we have these octahedral isomers where they're, again, kind of non-superimposable mirror images. And so we can kind of compare, right, with our groups. And so again, you can't rotate them to be the same. So right, they show the rotation, so rotated, not the same. And this is where molecule kits are super useful. So again, you probably played around with this in lab, but you know, if you need to take more time, borrow a kit, take time with the kit, you know, this isn't always easy to see. All right, so now we're going to take a baby look at crystal field theory here. And so crystal field theory, this gives us our HOMO-LUMO gap generally with our metals. And so generally how this is separated is on our bottom is, and so when we're looking at this, we're only looking at like a small piece of our MO diagram, right? We're just focusing on our d orbitals. And so these bottom ones are going to be our formally non-bonding d orbitals. And then these ones that are actually elevated are going to be the anti-bonding orbitals. So they may not be filled, so we'll see, right? Or they'll be, it's less favorable to fill. Yeah. So non-bonding means that they have like no pairs, and it'll kind of make more sense as we look at this. So as let's look at this in a little bit more detail. So this is the octahedral crystal field splitting diagram. I should have mentioned that. So this is octahedral. Like I said, or like we kind of touched on Tuesday, right? The geometry dictates the order of these. And for octahedral, it's still easy enough that we can, what I would say, like look at it. And so, okay, these are anti-bonding orbitals. And let's kind of draw out what they are. And so that's going to be your dz squared. And then you could kind of think about, well, how would this bond? And just looking at your z, we could draw how your ligands would go. And so there would be something like this. And then the donut is filled. So this is an example of a bonding orbital, right? Mainly focus on this z squared axis. And then, right, like I said, this is anti-bonding, so we're not focusing on them. So our bonding ones are down here, right? So this is dz squared bonding, and this is going to be ligand based. So right, this is that. And then we have our x squared minus y squared. We'll think about what that looks like. Right, so x squared minus y squared is on the xy axis here. And then that matches right with your middle scenario. So the x's are irrelevant, but then we'll have them shaded like that. So that's what we mean is like, okay, visually we can inspect this and it looks like they match. when you go on to inorganic chemistry, if you do take inorganic chemistry, you would do the whole irreducible representation shebang and prove this by math, but we don't need to go there today in this class. And so again, we're just appreciating, okay, so that's how we got that these are then corresponding to our antibonding orbital, okay? And then let's look at one more geometry that we're going to look at, again, for our Gen Chem purposes. We'll save all the others for higher levels classes. But the tetrahedral one is also easy to remember just because it's your octahedral one but flipped. So it's the opposite. So now the dx squared minus y squared and the d z squared are our non-bonding ones. So they don't match with anything. And again, you can kind of, tetrahedral is a little more difficult to visualize in your mind without doing the irreducible representations, but that's okay. So xy, xz, and yz. So you can kind of imagine them interacting with our planes evenly. And so again, this is our anti-bonding. All right, so what do we want to take away then? So what we're interested in is we're interested in this energy splitting here. So this is our crystal field energy splitting, and so we want to calculate this energy. And so basically this energy corresponds to the pretty colors. And so that's the other whole thing about these transition metal complexes is, again, this gap is going to be in the visible region, right? So like I've mentioned, for our organic compounds, maybe we kind of got this sense in our TLC lab, right? But they are UV active, right? So remember that. So their transition is in the UV range. All right, so let's go back to looking at these. Do we have, oh, and then, okay, so here's our equation. So we might want to figure out, what wavelength corresponds to this. We might want this formula, hc over wavelength, where h is Planck's constant, if we recall back from first quarter. And so now it's just kind of showing, how this works. So we have our ground state, and then again, excited state. So anything relaxing back down gives us our colors. And then, other things to keep in mind. So, okay, and that's what we'll look at with this. So it says our absorption spectra of this titanium hexaaqua compound absorbs in the kind of green, yellow region, And so then it's going to be the opposite color. So that's the other thing to keep in mind. So, okay, this is a red purple complex. So it looks purple, and then this means that its transition is a little bit smaller. But let's look at this. Okay, and then so where we're also getting at is we want to predict whether a compound is high spin or low spin. And so all that means is depending on this splitting, and we'll look at the trends too on what causes the splitting. But depending on this, so if it's very high, so if our crystal field splitting is large, then we tend to have what's called a low spin complex. So it's not going to be favorable to put electrons in these orbitals. So instead it's going to pair them, So basically, if we're quantifying this, we would say, okay, well, what is the price that we pay for pairing versus what is the price to put it in this higher energy orbital? And so sometimes for these low spin complexes, again, this gap is large that they pair on these lower non-bonding orbitals. And then if our gap is smaller, that could result again, potentially in a high spin complex where these electrons are promoted up here. And so then that's something that you'd want to, again, kind of test. And this would be both in like here in like a test setting, but also in the research lab setting, right? That's going to be something that you're asking yourself in the research lab. Well, is my compound low spin or high spin? How do I know? And so some of that could be as simple as, so in this case, right, our low spin complex is diamagnetic. And so remember, that just means we have all paired electrons. Versus if we had made a high spin complex, this would be paramagnetic. And then there are tests that you can do. So depending on the compound, sometimes NMR could tell you. So diamagnetic gives you like a sharp spectrum. Versus paramagnetic, it gets stretched out because of these unpaired electrons. There's other techniques like EPR for like iron metals or anything that is sensitive to iron, to EPR. All right, so then we can compare. And so let's start with this example here. And so we have our cyanide complexes. So looking at this iron octahedral cyanide complex versus this iron octahedral fluoro complex. And so before we get to this spectrochemical series and what this means and all this, let's just look at this. And so we'd want some data. So that's kind of what we're missing here is, well, what color is this compound? But based off of the color, and we can do an example, but based off of the color, right, this gives us our difference in energy. And so if we had a large difference in energy, or maybe if we were given this hint that it's diamagnetic, well, we can fill it in. Well, let's get our electron count, though. So it's iron. This complex is 4- overall. The cyanide is 6 of them. So what's our iron oxidation state and D count? What'd you say? So 2 plus, right? So Fe 2 plus, and then what does that make it for its D count? So remember, just count your periodic table, and you can use the big numbers in the middle. Then it's 2 plus. So right, iron, it's under 8 here. So it's D8 normally, but then 2 plus gives us, yeah, D6. So then this is D6. And then that's how we get this diagram, right? So we could kind of rewrite it. So octahedral, right? Again, octahedral complex, that gives us this. So this is just the definition of the octahedral splitting diagram. And then we would have to be given some information, like either the energy or telling us that it's diamagnetic. And probably that would be the best hint. So then it's diamagnetic. So we know we have to fill it in such that it's low spin. And then part of that is getting in to this spectrochemical series. But let's keep looking at this. So we can see that cyanide is over here, that it causes a large energy gap, and so we tend to see low spin complexes. Again, that's kind of the rule, but there are exceptions, as always in chemistry. Then if we look at our other type of ligands. So looking at these, right, these are more kind of X type. And so now they're going to have a smaller octahedral splitting energy. And so fluorine or fluoride, for example, they might tell you that it's paramagnetic. And so that's how you know, well, it has to fill in high spin. And that means, again, that our gap is small. So we're going 1, 2, 3, 4, 5. And then now we can go back and pair for 6 there. So let's look at a few complexes and kind of appreciate this. And so let's start with this cobalt species. So let me pull up, sorry, my camera for a second. So you probably have to draw, yeah, like the octahedral, and you would just draw this out, but we'll do some practice. Uh-oh, okay. Come on. Any day now. There we go. Sorry, trying to do some camera work, and then let me pop this out. All right, that should work. And so let's see how this goes. So I tried to drag over the whole lab, as you can tell. And so let's kind of look at what's going on. This isn't the perfect, ouch, this is hot. Okay, I'm losing my water. I should turn this off. All right, so let's look at what I have here, and then maybe we can reverse this reaction. So I have our test tube, and like I said, I apologize for not being the most flashy demo today, because all these things were being kind of a pain to get going and look correctly. And so all I did was take some cobalt chloride and dissolved it in water. And so that tends to give us, at least in some amount, this cobalt hexaaqua species. And so it should be pink, but it's also in equilibrium. And now I'm thinking about it that this is not the greatest example for reasons we'll see why in a second, but we can still go through it. So then we're given this species, so cobalt's still 2+, right? So we haven't changed oxidation states, but we can look at what's driving our color. And so what I did, like I said, for kind of the interest of time, and now we'll swap them. And so this is blue. And this is an endothermic process, so I should have put heat here on this side. But basically, if we add some acid to it, and so both of these actually have acid, it's just that this one is cold, and so it's still in this hexaaqua species, and it's pink, and maybe we can make some predictions, right, about its splitting energy. And then versus this blue complex, right? So then now we push our equilibrium, and that's why I was heating it kind of before class so it would actually be ready and be vibrant. Oh, where did my camera go? And so, right, so now we can tell, okay, that is a nice dark blue color. But let's discuss this dark blue color a little bit more. And so let's look at this in the context of our spectrochemical species, right? And so now it's dark blue. And so what do we notice about this? So what does it say about chloride? Yeah, so high spin and then low, right? So it's going to be pretty small, that transition. And so let's at least think about how it translates to the color, and we'll try to indeed verify that it's high spin, or at least again predicting. And so this is something that we want to keep in mind. And so I'll draw, so I assume this is tetrahedral. Now I'm not actually sure. Well, I'll assume it's tetrahedral. Well, let's assume tetrahedral, right? So then it's going to have a flip diagram from our octahedral. So 2 on bottom, 3 on top, so our non-bonding, and then XY, XZ, YZ. And so again, we're predicting a kind of smaller energy gap. Let's try to fill it in. So what do we predict, right? So let's look at our periodic table. So it's cobalt. So it should be cobalt 9, right? But then it's cobalt 2 plus. So how many electrons do I have? 7. And so they're both D7. And then again, just trying to maybe predict what it would look like. So we predict high spin. So 1, 2, 3, 4, 5, 6, 7 potentially. Again, with a small energy gap. And so let's think about the color now. And so we've created this nice, I mean, it almost looks purple. We'd have to plug it into the UV vis spectrometer, right, to get the exact wavelength. But what do we remember about the color that we see versus the energy? Yeah, so that's the part that I'm looking for. So whatever it's absorbing, it's the opposite, right? So let's think about that. And that makes sense for what we're saying, right? So we're saying, okay, it should have a low energy gap. And then it's this blue color, right? So blue or purple is usually high energy, right? We think of it high energy, but that's if it's absorbing that. And so since we're seeing that color, so right, we're seeing this with our chloride. And so this is implying we have a smaller energy gap, right? Since it's not absorbing the purple. So the purple, right, is a higher energy, but it's not absorbing that. So rather, it's absorbing the lower energy. So that's a good prediction. And so let's kind of, again, surmise for the cobalt. I'm not quite sure since water is kind of in the middle, right? So it could either go high spin or low spin, depending. But we could make some predictions. So again, this one's now octahedral. So I'm going to draw it in the opposite order, just kind of sketching it out. And kind of either way, so right, we could kind of do assume low spin, and then we fill it up 1, 2, 3, 4, 5, 6, but then we still have to put 1 up here. So maybe. Or we could do, what if it was high spin? So now just assume high spin. So 1, 2, 3, 4, 5, 6, 7. And so then there's a question of, do we have a spectroscopic technique that could differentiate between 1 unpaired versus 3 unpaired electrons, which I believe You could do EPR with cobalt, if I remember correctly, as well, or some sort of metal technique that would tell you the difference. And so again, right, just kind of putting your research cap on. And then the pink is maybe kind of suggesting that it's kind of higher in energy, right? Again, just kind of thinking about it. So now we're seeing the pink. So the pink is going to be on the lower end. Let me put our camera back, right? So pink is kind of towards red, I'm thinking, right? So red is the lowest. So then if it's showing us what it's not absorbing, maybe it's absorbing something high, right? So I would expect it to have a pretty large energy gap, again, comparatively speaking. So let's do a review, and then we'll keep playing with these other compounds that I brought. And so this could be, again, right, what you're doing in the research lab, or even in our lab, right, with you could put these chemicals into our UV vis, we could get the wavelength. And so let's say we did that, and let's say that we measured our wavelength, again, kind of our max absorbance at 480 nanometers. And so then we would say, what is the octahedral splitting energy? And so I'll rewrite the formulas for you in case you don't remember. And C, well, you can use 3 or 2.99. Then I'll write out Planck's constant as well. So see if you can plug it in, and then looking at your units of Planck's constant, right, you should get energy in joules. I believe that's the units for Planck's constant. Nope. So remember, nanometer is 10 to the negative 9. And then I forgot to mention that this cobalt reaction is reversible. And so I went ahead and stuck the hot one in the ice, and you can already see it's changing. Hopefully I don't break the glass. So I see chat has an answer, so we can plug it in. And I'll do a lazy conversion as well. So 480 times 10 to the negative 9. And so I got what chat got. Did we all get that in here? So I see yeses. We didn't get it. Ask me now. So 4.14 times 10 to the negative 19 joules there for our energy transition. And so again, that might be something that you'd want to quantify. All right, so let's look at a few other complexes and hopefully appreciate our spectrochemical series. And so again, I'll admit that I didn't, the demo I think is not as flashy as I wanted it to be. I looked at the prep and, well, the prep made it sound like the synthesis would be a little faster than it, well, no, I lied. The prep said it took a while, and I was like, let's try to rush it, and it didn't work. And then if you wanted to actually do it properly, it would take a long time. But let's look at some different species. Sorry, now I can't find what I'm looking for. Okay, so let's start off with, again, we're just appreciating our difference here. I should have gotten another test tube rack in retrospect. That's okay. All right, so we have, can we see that? So I'm trying to show just our nickel chloride species. And so this is just from the bottle. And we want to compare kind of relative. And so we'll kind of see. So we have this like nickel chloride, but there could be some water complex. I'm not like entirely sure. But just starting off, again, how you make it is we have this nickel chloride, and this is the hexahydrate. So you can't go between the hexahydrate and the anhydrous very easily. So this one takes refluxing in toluene. But if you just take the hydrate one and dissolve it, you should get this green complex. And so now looking, let's see if this follows what we expect. So that's what I was saying. Let's see how this goes. Maybe let's copy this again so we can see what we think. And so then I made, which took, this one I could actually do again if I had to. And so now we have this blue species. So this blue one that I have added, and there's probably like nickel chloride at the bottom. You can see there's a bunch of green stuff. But I think for the most part, this has turned into this nickel ammonia species. And so the ammonia is now more blue. Again, just kind of seeing, does that make sense? And then other ones to compare to. So let's see, where did they go? So this one didn't go as well as I had hoped. So it said to just add the counter ion, but it didn't quite work as quickly as it was supposed to. So this is with potassium thiocyanate, yeah. But it just kind of turned this darker green, so we can tell that something's happening. But it's just, I think it was supposed to be purple, so it's not happening as quickly as I would like it. I try to make a, well, like I said, we don't have ethylene diamine, so I added hexamine diamine, which is the 6-membered instead of the 2-membered chain, but I don't think it worked as well. It made this weird green paley compound. So that was kind of fun. Then I had one more. Are you the one? Yes. And so I think it's just really, really slow. And so now let me take these out for comparison. So it's kind of hard to tell, but this is lighter than our green one. So this is, right, nickel chloride on top. And then I added iodide, and it was supposed to make it yellow, and I feel like it just barely lightened it. But just kind of implying, right, from our spectrochemical series, that maybe this would be more low spin. So it's like kind of yellowish. And so then we could kind of compare it to our electromagnetic spectrum and see, like, does this make relative sense? There could also be, right, high spin, low spin effects. But again, just kind of looking at it. Oops. Oh my gosh. And so it kind of makes sense for some of these, right? Like I would expect, well, actually I would expect iodine to be more like blue or green or something. But again, we'd have to look at the geometry of these. But that's what's causing, again, all the different color is the difference between them. So it's absorbing kind of the opposite. Yeah. Other way. So I don't know that this. Uh, so so low. Sorry. So yeah, you said low spin. Yeah. So low spin. Sorry. So low spin should absorb higher energy. A shorter wave. Yeah. 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 So it absorbs higher energy, but then we expect it to be like red or yellow or something. That's why I'm like surprised by this one being yellow. But it's absorbing that, which means it's displaying. So yeah, it would absorb blue or violet, but then I would expect it to show yellow, which is why I'm kind of confused by this species, but uh, we need a proper MO diagram discussion to maybe get into the colors more and what's actually going on. But that's just a general trend, and then we would expect our low energy to be kind of violet as it absorbs the low energy, but I don't know why that wasn't quite working out. And then I was later looking up that there are better ways to synthesize it, but we don't have everything. And then I did play around. I wanted to see. So I made this cobalt amine complex, at least. So the cobalt amine complex is kind of bluish. So we could try to see if that makes sense. All right, we're kind of running out of time. Let's look at something else that I at least wanted to touch briefly on. So we might do some more review. But I did want to discuss kind of why this series is the way it is, or at least some other little points. And so the main other thing is, so like iodine, bromide, chloride, fluoride. So these are all just more of our kind of sigma donors. And so now let's think about what's special about CO, which I think we had kind of briefly talked about it, but we'll discuss it again. And so it's this concept of pi back bonding. And so now we have to think back to our CO, right, Lewis dot structure, or MO diagram. And so basically it has, right, our anti-bonding orbitals available. And so then these anti-bonding orbitals, right, so our pi anti-bonding orbitals kind of match in symmetry with our metal d orbitals. So then I could draw them like so. And then we get what's called this pi back bonding interaction, where then our carbonyl is donating back to the metal, and they have this extra interaction, and the metal's donating right back to the carbon. And so that really then causes a larger energy gap. Right, so now you have this pi back bonding effect, and so then that causes your anti-bonding orbital to be even higher in energy, right? So this is favorable, that would lower it, but then when we look at it, right, again, we're looking at the anti-bonding, so it throws it higher in energy. And so that's what gives us our larger split there. All right, we'll probably stop there for now. We can keep playing with these complexes. We might need to order some stuff so we can make cooler things. Any other questions or anything? All right, so I have the quiz, and then wherever the models are, they can make their way back. And then I swear I hit print both sides, and then it's still printed on two sides. So I have the staples out, so please staple your quiz. And then if you need it emailed to you, let me know. Otherwise, we can play with these metal complexes. I'll hang around on stream.